Here are selected problems from the section 6.4 in the book. They use the derivative notation that shows what you are differentiating with respect to. So they want to make sure that you know we're finding the derivative of this function with respect to x. So the variable is really up here. When x changes, you run the integral here. The only reason why they have a t is so you don't get the x's and the t's mixed up. Okay, so x is the variable. So what is that derivative? Well, you might think of getting an antiderivative for arctan t squared, which we haven't learned how to do, and which is either very difficult or impossible to get a closed form. And then you would, if you got one, you would evaluate it at these limits and then differentiate it. But using the second fundamental theorem of calculus, we recognize that inside function as a construction of an antiderivative. And so this is what we do. We know that capital F of x equaling this is an antiderivative for little f equaling this, because a can be any value here, so it happens to be 0.5. So we know that f prime of that integral is little f. So if we take the derivative of that integral, which is what this problem called for up here, we're just going to get that little f function, which is arctan x squared. So that's it. So the derivative of the antiderivative construction equals the original function in the integrand. Going on to number 11. Using this, it's the same kind of problem, except it has this extra wrinkle of going from x to 1. The construction says from a to x, not x to a. So we're going to turn the integrand, or the limits around, and when you do that, it just makes delta t's go backwards from the other version. Instead of going from x to 1, you go from 1 to x. So the integral is just going to be the negative of the previous integral. That's why you get this little negative there. That happens anytime you turn around the limits of integration. It flips the opposite sign, because again your delta t's are incrementing the opposite direction as they were for the other limits, which changes the sign. Anyway, so now we just realized that you can factor out this negative 1, just right here, and then write the notation again. Now you have it all set up. The derivative of this constructed integral, this constructed antiderivative, the derivative of it returns to the original function, log x. And you don't say log t, you say log x. Then the negative 1 times that is this. Now going on to 17. Write an expression for f of x such that f prime is sine x over x and f of 1 equals 5. So we don't know how to integrate up sine x over x. It would be very difficult anyway, if not impossible. So f of x is equal to, which is the antiderivative of f prime. We construct it by the second fundamental theorem of calculus. But we add on a constant, because if you take the derivative of the constant will be 0 anyway and return you back to the original function. So because we were given f of 1, we're going to let a equal 1 down there. So that's important. Because you have a 1, you're going to be able to use it by saying a equal 1. So a equal 1 is down here. So now your antiderivative looks like this. Now you say, well, 5 is f of 1 You could write that out in a different way, but anyway, 5 is f of 1. F of 1 is 1 to 1. The x value goes up there. And when you run an integral from the same limit to the same limit, it doesn't have any change at all. It's 0. And that's plus c. So c equals 5. C equals 5. So when you write it out, you get the antiderivative to be this. It has all the properties asked for. Its derivative is sine x over x, because the derivative of 5 is 0. F of 1, when you plug in 1 and put 1 up there, and you go from 1 to 1 is 0. So it all checks out. Now let's go down to one more problem here. That's problem number 25. Find g of negative 1 if g prime is cosine of x squared. Another difficult integration. G of 0 is negative 3. So because, well, we set up our construction, second fundamental theorem of calculus, we add on a c to accommodate getting this negative 3. Then we let a be 0 because 0 was where the information was given. So we're going to use the a equals 0. Rewrite what we have for the antiderivative. Plug in at 0. You plug in the 0 right here. 0 to 0. That integral turns out to be, well, is 0 because the limits are the same. There's no change there. And you're given that g of 0 is negative 3, so that means c plus 0 is c has to be negative 3. So then you write out the function. So then they say, where is g of negative 1? So g of negative 1 is putting negative 1 up here in the upper limit, and so that is the exact value of the expression. This expression right here is exactly what g of negative 1 is. Now if you wanted to approximate it, you'd run the integral program, get this number, subtract out the 3, and get this value here. So g of negative 1 would be approximately this value here. You could, if you didn't want to run this program from 0 to negative 1, if that made you nervous, you could just factor out the negative 1, change the limits around to go from negative 1 to 0 instead of 0 to negative 1, and everything would work out the same.